Hello, so we're DJIRIS. I'm Dina Barolas. I'm a freshman and I plan on studying mechanical engineering.
I'm a Kwazi Owusu-Achao. I'm also a freshman. I'm studying mechanical and electrical engineering.
I'm Alberto Hernandez, also a freshman, majoring in physics and mathematics.
Hi, I'm Victor Lopez. I'm a freshman and I'm planning on majoring in computer science and mathematics.
Hi, I'm Juan Rodriguez. I'm from San Diego. I'm going to be majoring in mathematics and computer science. And I'm from San Diego. I'm still from San Diego, yeah.
I don't like mics. We know it's been a long day and we're super late in the evening, so we're trying to keep it as engaging as possible so you guys are contained and motivated to keep listening to us. So with that in mind, I'm going to pass it over to Danielle to start us off.
Okay, so I know you guys have heard it a lot before, but I'm just going to say it again. So the first challenge is, we had to fly the quadcopter through 5 different hoops of different size and a pentagon shape. And then on the second challenge, we had to fly the quadcopter to different stations, 5 of them. 1 of them we had to avoid, 2 we had to take pictures of a poster, and the other 2 we had to interact with chemicals and identify which chemical that was. The chemicals were, as you know, were Clorox or Windex. Okay, so before we even started, actually attacking these challenges, we had to, decide where we're going to meet and when. Decide what times were convenient for everyone and where it would be, available for everyone, easily accessible places. So we had to, schedule around everyone else's, personal events, class or some other events. And then once we did actually gather, we basically started spilling out all the ideas we had on how to attack each of these challenges. Things, interesting ideas, creative ideas. But then after that, we had to decide which one of these were actually feasible. Which ones could we actually do with this time constraint, with only these few weeks to do these tasks. So for example, we wanted to use a Raspberry Pi for video transmission. But then we decided to discard that idea and instead use a transmitter and receiver that would improve the GoPro's latency, which, as you know, was about 5 seconds. And then once we got that done, we decided to divide all the responsibilities. So, let's based on interests or your skill sets. So, like me, I wanted to build something, so I wanted to help building, a stand for the Arduino and for the circuits. Or if someone was good at coding, like Miguel or Alberto or Victor, Quasi, they could help with the sensors. Or if you wanted to do autonomous, to do autonomous. And now Miguel's going to continue on with how we attack the first challenge, the obstacle challenge.
I said my name is Juan, but my middle name is Miguel, and I go by that, just to clarify. We decided to go with automation, fully autonomous, with the use of a first-person view camera. Sitting back there, I was thinking, what should I emphasize the most in my short amount of time that I have up here? And I guess I want to emphasize the idea process that we took and then break it down into little subsections of challenges that we have to tackle, which is a process that can be kind of generalized to any sort of project. We decided to essentially achieve full automation by having our programming our quadcopter to go through a destined course, since we are given the coordinates beforehand. And since we have to go through hoops, we do need some sort of mechanism to adjust ourselves accordingly to go through the center of the hoop, or else if we kind of guesstimate, they'll just end up crashing on one of the ends, and errors will probably carry forward as the course progresses, and we needed a feedback mechanism to correct that. So the first challenge was trying to get us to communicate with the quadcopter. As other teams have expressed, the quadcopter, the DJI Phantom, which is the quadcopter we used, is really user-unfriendly when it comes to hacking, essentially, because it's so closed off to any sort of, open source or integration of our ideas. So we thought, how do normal people control quadcopters? Well, with the joysticks. We took a close look at the joysticks by opening up the remote, and we saw that joysticks are pretty much just 2 variable resistors that send in voltages into the remote. what we decided to do is pretend to be those joysticks by sending in the voltages that, for example, pressing this remote, this joystick to the left would send. So the joystick to the left would send, I don't know, 3.3 volts into the signal input right here. We instead would tell our Arduino to send the input right there of that voltage. Easier said than done. We had to figure out a way of pulling that off. Our method was initially to create a digital to analog converter for Arduino, because Arduino only outputs digital. And when we started carrying that out, we faced some complications in the fact that the parts necessary had to be really precise and really specific, and we would not have had enough time to order them and have them come in 2 weeks. And so we scrapped the digital analog converter process and instead decided to go with pulse width modulation, which is a feature of the Arduino that lets you kind of pretend to be an analog signal by turning off a signal between 0 and 5 volts multiple times over a duty cycle such that it looks as if it is, I don't know, for example, if you want to achieve 2.5 volts, you just half the time you shoot up 5 volts, half the time you shoot up no volts, so that the average is 2.5 volts. That really expedient process, turning off between 0 and 5 volts, requires you to clean up the signal a little bit before it goes into the microcontroller. And for that, we used low-pass filter circuits for each PWM output. And after using a multimeter, we found out that it was pretty effective, and we did actually achieve communication with the controller. After that, we needed to tackle the problem of having the quadcopter analyze the hoop and then go through it, adjust itself, and then go through the corner. To pull that off, we had, I'll address the last 2 points first. We had the GoPro there, but as other teams have mentioned, there's an issue with lag with the GoPro signal, because whatever the GoPro sees, we'll see 3 seconds later if we just use what we were given. So what we decided to do is buy a radio transmitter receiver that we would mount on the quadcopter and connect the receiving end to your computer. And with that, we were able to achieve a lag of about, it was like 10 nanoseconds or something, which was extremely useful because it was almost instantaneous feedback video-wise. Once we did have a video feed, we could then analyze the images from MATLAB, essentially take the current frame, send it to MATLAB, process it so that it becomes a more simplified image with just the hoop. Then use that to find the center of the hoop and look at the center of our image and see, do we need to go right? And then adjust itself a little bit left and then adjust itself vertically to be at the center to go through the hoop. With that, we created some functions in Arduino, in the Arduino language. I'm not really too sure what it's called. It's called Arduino. That essentially are 4 main functions: go left, go right, go upward, go downward. It would take MATLAB's information as to where it is with respect to the hoop, and then it would tell the Arduino to execute that certain function to make the quadcopter adjust itself accordingly until it's at the center of the hoop. And that essentially was our process to achieve full automation. Next slide. On the day of, well, a couple days before, okay, so our tragic flaw happened at the beginning, essentially. We got our quadcopter the first week, and we wanted to play with it immediately. So we went to like the auditorium, Kresge, and we built it, and we were really impatient, so we couldn't get it to calibrate. And after like an hour of trying to calibrate it, we just gave up and started playing with it. And we neglected the fact that it wasn't fully calibrated. So when we had the whole mechanism that I described beforehand all in place, unfortunately, since it relies on the quadcopter to be stable, to sort of get adjusted left and right, up, down, and whatnot, the quadcopter would never stand still, even with our manual control. So if you just turn it on and elevate it, it'll just start drifting to the left and then downward and kind of spiral and just kind of die. So unfortunately, our ideas were based on idealistic understanding or misunderstanding that the thing would be able to hover on its own in a steady position if no one messed with the remotes, which I don't feel was a too unrealistic expectation, but is something we should have thought of beforehand. So as a result, we went with manual flight, which is just us telling the quadcopter with our remotes where to go, fly this way, fly that direction, make oops, and I feel like we did pretty well in the first obstacle course of the competition. And with that, we're going to turn it over to Victor to describe the second challenge.
So, when designing our approach to the second challenge, we quickly saw that due to the amount of response and input the quadcopter would need to perform the challenge, we would go with a manual approach as opposed to an autonomous one, so that we could properly tell it what to do and when to do it. So the way we decided to know where the quadcopter was without having to exactly look at it was like many other teams did. We used the GoPro and had a live feed feeding us the view of the quadcopter. And the way we did this involved a video transmitter and receiver so that we can cut down the latency of the GoPro and actually get the transmission which within thousandths of a second, which was ideal when flying. So to speak about the sensors is my partner Aquasi.
Thank you, Victor. So for the sensors part of this competition, what we had to determine was think about how to pop these balloons in the second challenge. And so we came up with a couple of designs, and what we came with actually was creating this needle with a spring attached to it, which actually we came up with kind of out of accident, which is pretty good. But the good news about this design is that what happens is that it creates a bit more force on the balloons themselves, so that when we come up to pop them, they wouldn't move away, as was one of the challenges with this challenge. And we decided to put the chemi resistors near these poppers so that they wouldn't be near the propellers for the quadcopter, and so that they'd be able to sense the chemicals. And also we decided to put the Arduino on, I'm not sure if you guys see it, but this area of the base here. That way we can create like a radial kind of design for our circuit a little bit. And in order to actually program our Arduino to sense the circuit, we decided to use two LEDs. One that would, the white one, it's right here, but it would be used for Clorox, and the yellow one for LED for Windex. And next slide. So basically what we use is like the concept of a voltage divider, in which we have we have like the current go through these two areas of our circuit, and the first two resistors here represent the chemi resistor, and what we would do is find potential after the chemi resistor before the quadcopter interacted with the chemical, and then after it. And it was actually pretty useful to do this because when we found out that Clorox actually decreases the resistance of the chemi resistor, it increases, and Windex increases it, which creates a change in the voltage drop of the chemi resistor, which changes the potential that we were reading. So what we did was take the difference between like the first and second readings of potentials and subtract them, and depending on the difference, we could determine which chemical was present. And on a side note, actually during the competition, although our battery became really low and we couldn't really get to the height to pop the balloons, we tested the chemical resistor later and it worked pretty well, which is a plus for us. And now I will pass it on to Alberto, and we'll talk about what we learned.
Yes. Now I get to talk about all the important skills we learned from this 4-week adventure. As you guys can tell, it's a pretty tough challenge to throw at a bunch of freshmen who are a few weeks out of their first semester. But I think we did pretty well. We picked up some very good technical skills along with some soft skills, interpersonal skills. Oh no, it's coming. Thanks. So we did a lot of Arduino programming, whether it be to manipulate joysticks or whether it be to read the voltages across the chemi resistor. Other people have mentioned the C-based language. This is very useful if you're trying to work with any other piece of technology that exists that has a microcontroller, because now you know how to use it. Again, with the Kemi resistors, we had to design one that worked, and more importantly, design one that you can test, so that when it breaks, you can fix it. A lot of people design things that you can't really tell if it's going to work or not until the day of. The quality managed to put together something we could work with well. Circuitry, we have a much better understanding of circuitry. Following the user input to move the joysticks and how the signal feeds to the remote, feeds to the transmitter, goes to the quad tower receiving. We have to understand the whole process and see at which point we want to go ahead and cut it off and make it automated. And in the workshop, in the D-Lab, we did a lot of stuff with like using a bandsaw to cut this up, alligator clips, making prototypes. Would you like to talk about soft skills?
So in addition to these technical skills we gained, we also learned plenty about what we had to do as a team to complete the project. So when we started off, we had a bunch of cool ideas, all of which we were passionate about. But as a team, we had to compromise and decide on what we were going to do and how we were going to do it. And another skill we learned, or challenge we had to deal with, was like how many other teams said, was working under a deadline. We had a very tight deadline to follow, and as you guys saw in the video, I think we did decently well. And the final thing we really had to learn was understanding our limits. As I said, when we started off, we had all these really big ideas, but some of them we just couldn't implement due to our budget, our time restraint, or sometimes we just didn't know enough yet. So I'd like to talk about a bit of the practicality and utility of the quadcopter, some of the applications, if you will. So this quadcopter is pretty small as is, but we were thinking about how small can we get it, how big can we get it, and we've discussed this, and we've determined that the key issue here is the weight and getting it to actually lift in different sizes. So for what it is, this quadcopter is actually pretty ideal. This is also, our design would also be feasible to manufacture. Most of the hurdles of this challenge are once, and for example, the coding. Once we complete our code, it'd be easy to reproduce. Once we complete our design, it'd be easy to reproduce. And one of the applications is to remote detection of potentially hazardous chemicals, and potentially end up saving a life. And as I said, using the functions forward, backwards, left, right, up, down, we could potentially make a GPS independent quadcopter. So our budget was, we spent most of our budget on the transmitter and receiver because we wanted to really optimize the feed we would get. And we ended up using the $100 over the free supplies given to us. We would like to thank MIT Lincoln Laboratory for sponsoring us, and the OME and all the other companies who participated in the Momentum program. I don't know if you have time for questions.
Thank you very much.